that is in the Sinhalese or Tamil or whatever language that you use during A level. Uh, if you used English, of course, you should have heard about vectors. All right, so here we will be covering these things, vectors and their components. Uh, and the second one, unit vectors and adding vectors by components. Um, and the last but not the least is multiplying vectors. All right. All right. So there is some disturbance. All right. All right. All right. So first, maybe I will just, because some people may not have heard what vectors are, and that is the introduction and what are components. That's the first thing we will go through. And next, we will come to a little bit more advanced topic. What are unit vectors and how to add vectors using these unit vectors. And even more advanced topic is the third one, multiplying vectors. All right. And so first we will go through the vectors and their components. So these are the learning objectives. So during the lecture, you can, if you have any question, you can uh, type it in the chat box. All right. Vectors and their components. So in that, the objectives are, you will see what are vectors and how to draw a vector, and also how to add vectors by drawing them, right? Those things. And other thing is calculate the components of a vector on a given coordinate system, showing them in a drawing. So to draw the vectors and that is calculate the components. And the third objective is, given the components of a vector, draw a vector and determine its magnitude and direction. All right. So those are the things we will go through. All right. And vectors and the scalars. So to understand vectors, maybe first you have to understand, or that is, you have to also understand what are scalars. Um, so first we will go through the vectors. So some physical quantities in physics or mechanics or engineering or technology has a magnitude as well as a direction. So not only a magnitude, but also it has some direction. For example, the displacement vector here. Uh, Someone is raising the hand, I think. You can type in the question. Yeah, or you can ask it also. So the displacement vector is 5 meter. That is, for example, displacement is a vector. For example, displacement of 5 meter towards the north. Or force, for example, you have now already learned what is force uh, and what are the units of force. Like force is also a vector. So such quantities are called vectors. They not only have a magnitude, but also they have a direction. And yeah, I hear some disturbances. So vector quantity having a magnitude and direction can be represented by a vector drawing a straight line in the direction of the vector quantity. For example, if the displacement is 5 meters toward the north, then you can draw a line towards the north. Um, of course, you have to choose a scale because usually on a paper, it's difficult to draw a 5-meter line, right? So you have to choose some scale like 1 centimeter equal 1 meter or something like that. So vectors follow the rules of vector algebra. So you cannot just add vectors like you add just some numbers. Um, you have to use the vector algebra. And so these are some example vectors: displacement, velocity, acceleration, force, momentum. I think you already heard these terms, except for momentum. Uh, you heard about displacement, velocity, acceleration, force, uh, momentum. Also, the momentum is actually the reason I wanted to do the vectors because without the vectors, sometimes it would be difficult to understand about momentum. Uh, Sometimes, especially the angular momentum and also linear momentum. So that would be another part of this uh, content that is covered. Not all physical quantities have a direction. Such quantities having only a magnitude are called scalars. So opposed to vectors, if some physical quantity that is used in physics or whatever, the length, um, mass, time, so some quantities have no direction, right? Uh, so those quantities that are only having a magnitude are called scalars. So you have to clearly understand the difference between vectors and scalars. For some examples of scalars are temperature, pressure, mass, time, also energy. All are scalar quantities. They don't have direction that points. That is, for example, energy doesn't point at a certain direction, right? You know what is energy and you know what are the units of energy. You know what is the units of mass and what is mass and also time. They don't point. This word point is very important uh, in that is in spatial sense, that is in the space. They don't point in a direction. So they are scalars. So scalars are different from vectors. Vectors have both not only magnitude, also they have the direction, but scalars don't have any direction in space. Right? Any questions? All good? So this is on vectors and scalars. All right. Maybe I have to make it a little bit smaller. Okay, there you go. All right. Representation of a vector. So to represent a vector, you draw a line in a certain direction of that is in the direction of the vector with the length of the line proportional to the magnitude of the vector. For example, the force. You know what are the units of the force? Anyone remember? Standard SI units? Newtons, right? So if some force is acting on some object, then you can represent it using. So you saw this before actually, when you draw the free body diagrams and those things, you already, but now you can even further deeply understand the concept of vectors, not only in that is one dimension, but also in 2 dimensions or 3 dimensions. So this vector you see here, do you see my mouse pointer? Okay, I think you can see it, no? Yeah, the pointer. Yeah, anyhow. So maybe I can use the PowerPoint. I think you can see this, no? My mouse pointer A to B, it is showing as a cross. All right. Yes, okay. One student says yes. So, yeah, it is a bit tiny, but yeah, I can try PowerPoint, but it might make other problems. So somehow, yeah, A to B is a vector. For example, the displacement vector, like this one, something going from A to B. Then if the initial point is A, the final point is B. This is the displacement vector, the straight line. So despite the path traveled, it can go in a shorter path or more longer path. The displacement is right like x2 minus x1. Remember the delta x? Can check the previous notes or your short notes. So this displacement vector can be represented by this line. And you put a small arrow in the direction of the displacement. And this vector AB and A prime, B prime, and A double prime, B double prime, all three vectors are the same because they have the same length and they point in the same uh, direction. So these all three vectors are equivalent. They are equal. Okay. So this is the same vector representation. Show the distance between point A and B, the difference marks straight here. So this is here, figure B, that was figure A, figure B. Here, that is an example of a displacement vector. So the vector can be a force vector or whatever vector quantity, velocity, acceleration. Remember the acceleration and force are related by the Newton's second law, F equal ma. So F and A both are vectors, but m is a scalar quantity. Remember Newton's second law? Right. And adding vectors geometrically. So you can add vectors. There are several methods. One of the basic methods is you can add vectors geometrical. That is graphical. And so here it is explained how to add two vectors. For example, if there are two vectors, vector A and vector B, you can geometrically add them, that's graphically, on a graph sheet. Or so you can maybe, if you have a piece of paper or if you should have your notebook, you can try this. So here we will be considering first two-dimensional uh, space, two-dimension. Uh, right? So, so this is the vector A here, first vector. And there's another vector B. So we want to add them. So we use a so-called method to draw the vectors, the head to tail method, or the graphical method to add the vectors A and B. So when you add these two vectors, the resultant vector here is displayed as S. So in vector algebra, we can write it like this. A, vector A. So there is an arrow on top. That means A is a vector. This arrow, B is a vector, equals S. S is the magnitude of the resultant vector. That is the sum of the vectors. Okay. Resultant means the equivalent vector You can replace vector A and B by vector S. So if you are doing it on a piece of paper, you can also try this. You can draw the vector A, but you have to choose some scale. For example, like 1 centimeter equal 10 kilometers. That is a scale. So on the graph sheet, you have to write the scale that you are using. For example, a graph sheet similar to that you use in the labs to draw graphs. So there also you are usually using a scale, right? 1 centimeter equal 1 Newton, whatever, when you plot. Similarly, so the vector A can be represented on that graph paper. So if you like, you can try that. But since that is, you have to choose a scale like this 1 centimeter here, 1 centimeter, 10 kilometers. If you are representing some forces, maybe some of you did that lab, I'm not sure. All did, but some of you did the vector forces lab. In that, you have to choose like 1 centimeter equal 1 Newton or something like that. And you sketch a vector B, you draw the vector B to the same scale with the tail at the head of the vector A. So you put the tail of, so the vector has a tail and the head, the arrowhead. You put the second vector's tail at the head of the first vector. So, right? So that's why sometimes it's called the head to tail method. And you place the second vector such that the tail of it is at the head of the first vector. And you just connect the tail of the first vector with the head of the second vector. So that vector would be the resulting vector S. That is the way to add two vectors. You can't just add, like if I say add 5 newtons and 2 newtons, it is not necessarily 7 newtons, right? Because the final value depends upon the direction of each force. Do you understand what I'm telling? But a scalar quantity, of course, you can add like a 1 kilogram and a 2 kilogram mass. It would be 3 kilograms, right? But vectors, not always that. That is not the case always. Like 5 newtons plus 3 newtons is not always 8 newtons. All right. So you have to like vectorially add them in order to find the resultant vector. But there is a more easy method because always we don't want to use graph sheets and draw these things. First, that is, you can use unit vectors to add vectors more easily rather than using a geometrical method or graphical method. Right. So you can add two vectors, for example, vector A and B by placing them uh, head to tail. So sometimes this method is called the head to tail method. Uh, that is, you place one vector's tail on the head of the other vector, and you combine the vectors connected tail of the first to the head of the second vector here. So that's what it means. So finally, tail of the first vector and the head of the second vector, you connect, that is the vector connecting those 2 points is the resultant vector. In this case, it is the S. So any questions? So everyone good with this? So maybe some of you tried it on your notebooks. Just randomly draw vectors and try to add them. Try to do that. All right. So here, the length of S is the magnitude of the resultant. For example, if a 5 Newton force is acting or 3 Newtons along this vector A, let's say it's 3 Newtons, and this vector B may be 5 Newtons or 4 Newtons, then you can, yeah, yeah, this vector would be whatever that length comes out of your graphical method. So you have to use a ruler and measure the length of the resultant vector, and you rescale it, reverse the scale, and you can find what is the actual length of the resultant vector S. Yeah, you can think of two forces acting on an object, Also, or then how to add the resultant, so you can use the graphical method also. Everyone good? All right. And also, there is a component method, but before coming to component method of adding vectors, you have to know what are components of vectors. What are components of vectors? So here, uh, so component, here we have the vector A here again. Vector A, you see the letter A. Here we put it on the XY coordinate system, the Cartesian two-dimensional coordinate system. Uh, so the components of a vector, a component of a vector is the projection of the vector on an axis. So how many axes are here? Two axes, right? The x-axis and the y-axis. And the component along a certain axis is the projection of the vector along that axis. So what is this projection, right? Let's see. In the figure, for example, Ax is the component of vector of the vector A uh, along the x-axis. So this Ax is the x component of the uh, vector A. X. You see here X. Ay here is, uh, you see here Ay is the component of the uh, component along the y-axis. So if the vector, you move the axis forward, that is x-axis forward, this vector would be same way, but now again, this would be the y component. This would be the x component. So as you can see, the components are shorter in length compared to the length of the original vector A. See, they are smaller because they are projections. Like, for example, how can I explain? Like a shadow, for example. You put a torch on this side, and there is a vector here, and you see a shadow. So it's called a projection. So that kind of thing is called a projection. Uh, yeah. So the projection of the vector on a projector, you have seen the projector, right? So it's kind of, you're projecting the vector, but your image would be your components. So if you have a light on this side and project this, your screen on the x-axis, it will show a it's a shadow of this vector. So it's called a component, X component if it is along x-axis, y component if it is along y-axis. All right. Any questions? So this, so simply, since all parallel vectors are equivalent, I can draw the same thing such as in figure C. Yeah. So the vector A can be uh, decomposed into two components, the x component AX and the y component AY. So the AX is called, that is, AX and AY are the x and y components of vector A. So the vector is represented by, can be represented by its components. So the vector AX plus AY represents the vector A, because this plus this is this. Even graphic. Everyone now understand what is the x component of a vector and what is the y component. So to get the x and y component, you have to place the vector on a Cartesian coordinate system like the xy coordinate system. If you are on, that is, if you are in 2 dimensions, if you are in 3 dimensions, you can also use the z-axis. All right. And there would be a z component also. But here we, for simplicity, we just consider only 2 axes in 2 dimensions. Right? So these components you already learned during this drawing free body diagrams and those things you already learned. So if A was acceleration, then this would be acceleration components. But if A was the uh, force, then you can, of course, project it or resolve it into the force into its x component and y component. So if the vector itself is along the x-axis, then what would happen? What would be the y component? If the vector A is along x-axis, what would be the y component? Can someone tell me? If the vector A was along, that is, if the theta was 0, if the theta angle was 0, then what would be the y component of the vector? 0. One student has replied as 0. Everyone agree with that? So these are not hard things, but if you are planning to become some engineering technologists, then you have to have some idea about these things. All right. We just started, but we'll go through. So further into components of vectors, that is the x component, y component, like that. So that's the scalar components of any two-dimensional vector along the coordinate axes are found by dropping perpendicular lines from the ends of the coordinate ends of the vector onto the coordinate axes, and the components are given by this. So since this is the vector A can be broken into two components, x component broken or resolved or decomposed into two components, AX and AY. The x component can be written as AX equal A cosine theta. So that A cosine theta quantity for the AX is a scalar quantity, AX. So the vector is represented by two scalar quantities, AX and AY. AX is A cosine theta. AY is, what is AY? A sine theta. So where theta is the angle between the positive direction of the x-axis and the direction of whatever vector A. So A can be the acceleration or the force or momentum or whatever, or the displacement or the velocity, can be any vector quantity, but not a scalar quantity. It cannot be the time, cannot be the mass, because they don't have any direction, right? So for example, 5 kilograms of sugar doesn't have a direction, right? But the force has the direction, the weight, or the applied force on a mass has a direction. All right. Any questions? No questions. So this is a very fun topic, I think. It's not that difficult for you. You have done maybe harder things than this. The algebraic sign of a component indicates its direction, so, and the associated axis. So the sign of this indicates its direction. For example, if this is positive for x, if a cosine theta is positive, then that is ax is positive, then that means it is in the positive x-axis, direction of the positive x-axis. That is to the right side, right? Like here. So if it is negative, then for example, then it would be in the negative. You have to draw the arrow in the opposite direction. Same goes for the y component also. So if you know the components of a vector, so now you just learned how to find the components of a vector if you know uh, the vector, the theta, and the magnitude A. But if you also, you can go do it in the reverse. If you know the components of a vector, you can find the A, that is the magnitude of the vector, and the angle theta using this tan theta equal AY over AX, because tan theta is, remember, AY divided by AX, right? So you can uh, find the components if you know the magnitude and the angle theta of that vector. You can find the x component and y component. Also, you can do the vice versa. If you know the components ax and ay, you can find the magnitude of the vector and the angle theta. Of course, you have to take the tan inverse of this, the arctan, then you will find the theta. So now you know what is a vector, right? They have magnitude and direction. And you know how to add two vectors using the graphical method, the head to tail method. So same goes if you have more than two vectors, you will first add two vectors, then add it to three vectors, the third vector. So it doesn't matter you have 100 vectors or how much, right? Also now you learn what are components of vectors, the x component and y component, and how to transform a vector into that find the vector components, the x component and y component using the magnitude and angle of the vector, magnitude A and angle T. And also you learn how to uh, find the vector if you know the components Ax and Ay, for example. You just use the Pythagoras like formula. This length is Ax, this length is Ay. So this length should be Ax squared plus Ay squared. square root. The tan theta angle is given by ay, the y component divided by the x component. So if you know the tan theta, you can find the tan, that is the theta, taking the inverse tangent. Any questions up to now? No? So if you have questions, you can just type it in the chat box. So the fundamentals are the most important thing in studying any subject. Engineering, mechanics, or physics, or whatever, science, technology. Without knowing the fundamentals, you cannot claim that you have learned something. Because some people may be expecting that uh, just to make something and okay, I'm the technologist or whatever like that. Yeah, in academia, that doesn't happen. All right. So these are the most valuable fundamentals that you have to know in order to become an engineering technologist. Right. Uh, yeah, this is kind of an extra part, but this is very important. All right. I made it extra because of the usually limited time. Because once we did all the lectures in 6 weeks during the COVID period. Yeah, they're very scared. Just 6 weeks, 15 weeks lectures in 6. All right. So if you have any questions, you can ask me. So if you are really planning to become an engineering technologist or engineer, make sure you learn all this stuff, including these things. Maybe not for the exam, maybe for the exam, but right. One student said, no, sir. What is that? No, sir. I'm not sure what do you mean, no. You say no for something. Maybe that's something, I'm not sure. Okay, you have to be more specific. Uh, Maybe he means that he doesn't want to become an engineer or something, I'm not sure. All right, anyhow. Or maybe he means that he's, no question. Oh, I see, no question. Yeah, that's sometimes good, sometimes bad. Because having questions is sometimes very good. Because questions are the things that makes you learn, but sometimes if you have already done these things, maybe you don't have much questions. All right. Uh, Component science in different, but there are many students that who have not even heard the word vector. I have seen. Yeah, one student in the previous batch, he said he knows about vector, but not about vector. Yeah, very funny stuff happened. Yeah, that is, he knows to sing and those things and anyhow, component signs in the different quadrants. So here I put another slide. So depending on which quadrant you are in, the component sign changes. For example, so this is the XY coordinate system, and this is a vector here. If you look at the first arrow here. So in the first quadrant, if you represent a vector in the first quadrant of your XY coordinate system, then both x and y components are positive, just as the coordinates, because this is some vector, maybe the force, maybe the acceleration, maybe the displacement or whatever, uh, maybe the velocity vector. You represent it on a graphical way, then if it is in the first quadrant of your graph, then there are four quadrants here. This is the first quadrant. If you take the XY coordinate system, there are four quadrants. First quadrant is this one. Second quadrant here. Third quadrant is here. And the fourth quadrant is over there. The first quadrant, you see that both, since both coordinates are positive, so is the components. So are the components. So the both x and y components both are positive in the first quadrant. In the second quadrant, yeah, one student asking a question. Let's come back to that. Yeah, that's good question, but maybe I don't have a lot of time to explain that. You can use your calculator and try that. But of course, I will give some examples and tutorials, and you can uh, uh, get hands-on experience on what happens when the tan get negative. We will come to that. And in the second quadrant, very good question though that student asked, is a very logical question. Yeah, we will come to that maybe in the next example or also in the tutorials. Second, so if you have any questions, just drop it in the chat box. And in the second quadrant, what happens is the x component is negative and the y component become positive. Do you see it in your mind? Why the x component is positive and y component is negative? You will take the small angle theta instead of the large angle, because you can come to the second quadrant by drawing a large angle theta from, because usually you measure the angle from the positive x-axis to the whatever uh, pointing direction. We take the small angle instead of the large angle. So if we take the small angle here, will uh, more easy to understand. And in the third quadrant, what happens? Both x and y components, both are negative. Both are negative. Right? And in the fourth quadrant, this one, x component is positive, y component is negative because it's below the x-axis. Right? At the center, all components are zero at the origin. Right? Because this is the 0, 0 point of the x-y coordinate system. All right, so that is just about the signs of the components. So if it is pointing some vector force pointing in this direction, like in your xy coordinate, both x and y components both are positive. X cos theta and x sin theta both are positive. And maybe the force, for example, if you already did the lab, maybe you understand what I mean more clearly. Right? And if it is pointing this direction, then uh, the x component become negative, y component positive. That is a cos theta become negative, a sin theta become positive if you are pointing in such direction, and so on. Right? So this vector quantity can be represented by its components, and depending on which quadrant you are in with respect to the xy coordinate system, the sign of the components change. Right? So here there is an example. Maybe you can take a small that your notebook and try to answer this. So it is asking what are the x component and y component of 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 a vector in the xy plane if its direction is 250 degrees counterclockwise from the positive direction of the x-axis and its magnitude is. So there is a certain vector, theta is given. You can maybe take your piece of paper and draw the xy coordinate system. Just maybe if you have your notebook, you can do that. Just draw a small xy coordinate system and mark the vector 250 degrees counterclockwise from the positive direction of the x-axis, and its magnitude is 7.3 meters. So this one you have to scale it down because in your notebook you cannot draw a line 7.3 meters, right? Unless you have a very large notebook or paper, graph sheet. So you have to choose a scale like 1 centimeter equal 1 meter, for example. But when you just draw a sketch, you don't need to think about that also. You can just sketch it, right? But remember that you are actually scaling it. So if the angle is 250 degrees counterclockwise from the positive x-axis, which quadrant is it in? The vector? Can someone tell me which quadrant is the vector in? You can maybe sketch a little bit. Because 0 to 90 first quadrant, 0 to the 90 to 180, not the second, no? Good effort. One student said second quadrant, but second quadrant is 90 to 180. Third quadrant is 180 to 270. Fourth quadrant is, yeah, third quadrant. Everyone agree with this? One student put third quadrant, which is correct. Fourth quadrant is what? 270 to 360. So this is the large angle, not the small angle like here. This one I considered the small angle, right? I'm considering the total large angle. First quadrant 0 to 90. Second quadrant 90 to 180. Third quadrant 92, that is 180 to 270. Fourth quadrant 270 to 360, because 360 is the full circle. But here when finding the cosine theta, we will use the small angle because maybe confusing to you to use the large angle and use complex trigonometry to find the, so we can use the small angle. Here now it's the solution. Yeah, I put the updated notes. I updated it a little bit. So since the last one I put on the LMS, so maybe yeah, I have put the updated one. So you see the angle here is 250. So your vector is in the which quadrant? Third quadrant. But we are more interested in the small angle here. So what is the small angle here? That is the angle between the negative x-axis and the vector. Because this total angle is 180. So 250 minus 180 is 70 degrees. So now I can find my x component and y component very easy, because in the third quadrant, the x component is negative and also the y component is negative. Both are given by but a cosine theta. Put these numbers, get minus 2.5 meters for the x component, x, and for the y component, you use ay equal y sine theta. Uh, but I am using the small angle again. So instead of putting 250, I put 70, but with a negative sign. So it's 6.9. So those are the x and y components. Also, you can do the vice versa. If you know the x and y components, you can also find the uh, this that is the vector itself by taking using the Pythagoras law. Also, you can reverse this process. Here you broke it into two components, um, but also you can do the reverse, right? If you do the reverse, then yeah, depending on that one student asked, right? If you are in what happens if something becomes negative, tan theta become negative. So if tan theta is negative, of course, you are not in the first quadrant, right? You are not in the first quadrant. You either have to be in the, and yeah, you cannot be in the third quadrant either if tan theta is negative, because tan theta, the third quadrant also, tan theta is positive, right? Because negative divided by negative become positive. So if tan theta is negative, then that means you are either in the second quadrant or in the fourth quadrant, right? Yeah, you can think about it further by yourself. And also maybe I'll do the tutorial as soon as I finish these parts of the lecture. Uh, yeah, this week I'm not sure I can do it, but maybe I can give part of it so you can start working. Yeah, next, so we have done about vectors and components and how to come from, how to find the, that is components, and if you know the components, how to find the length of the vector, and that's the magnitude and the angle theta, right? Yeah, I will give you tutorial number 9, so you can explore that. Yeah, as soon as I finish these parts. So you can explore those things. What happens if tan theta is negative and those things. Yeah, without mathematics, there is no engineering actually, or technology. That is, mathematics is just the language of engineering or technology or science. It is, that's why STEM, we call it STEM. Yeah, now some people are inventing STEAM, but but yeah, it is originally STEM, because they all are related to uh, each other. Because mathematics is the language of engineering, technology, and science. Without knowing a language, you cannot claim that you know something, right? In science or technology or engineering. Yeah, but if you are just making this bull of cards or something, that's a different story. But you came to a university, right? Right. All right. And unit vectors. So the next part is unit vectors, adding vectors by components. So there's something called unit vectors, and you can add vectors using uh, that is using their components. That is the second one I mentioned. So up to now, you have learned what are vectors and what are components of vectors, those things, and how to add vectors. Uh, those things. Now, the next we come to part two, unit vectors and adding vectors by components. Uh, right. So convert a vector between magnitude, angle, and unit vector notation. So you can, so now you already saw what is the magnitude angle notation. That is, know the magnitude of the vector, like for example, 5 meters, and the angle theta, like maybe 30 degrees or whatever. So that notation to unit vector notation. So you can do this using the components. Already you, I think, have the idea, but uh, we specifically define some unit vectors, something called unit vectors. Uh, and add and subtract vectors in magnitude angle notation and unit vector notation. So that's the next thing you will learn. Uh, yeah, add and subtract vectors. So you can use the unit so-called magnitude and angle notation, which you already saw, and between that is use unit vector notation, right? Special unit vector notation. No? So that's the part two that you will be learning. So what are unit vectors? Unit vectors. So vectors you know, but what are unit vectors? So what is a unit? A unit usually means one, right? Right? Like 1 unit of electricity. That's not this vector quantity, but I'm just saying, right? Uh, so unit is usually it represents a magnitude of 1. Unit means that 1, exactly magnitude of 1. So the unit vector has a magnitude of 1 and it points in a particular direction. So what are the directions you know in the Cartesian coordinate systems? You know the x direction, y direction, and also if it is in 3 dimensions, you have the z direction, right? So what the unit vector does is it just points along each direction. So these vectors, I hat, you put instead of putting a line on top of the vector, you put a small hat. I hat, j hat, and k hat. If you are in 3 dimensions, so they just point along each axis. I hat points along the x-axis, j hat points along the y-axis, k hat points along the z-axis. So that is if you are considering 3 dimensional stuff. Most of the time we use 2 dimensions, the x-axis and y-axis. Right? But sometimes we also have to use 3 dimensions. Maybe rotation, yeah, those things. In angular momentum. So that is one of the reasons, this angular momentum. I wanted to do the vectors. Yeah, but of course, you can very well study all the tutorial discussions up to now. But maybe I will put some tutorial number 8 answers also. Yeah, you are good to go. But yeah, these things also you have to know. All right. Right. So you use a hat. Hat is this hat on top of each vector. So the sole purpose of using this unit vector is to point. If you want to point along x-axis, you use the I hat. What is the magnitude of I hat? Anyone? I hat is a unit vector. Magnitude of I hat? Anyone? Have you been listening to me? 1. Yes, at least one student has been listening to me. Some people might be having their lunch. I don't know. Yeah. All right. And right now you understand that. So J hat also magnitude is 1, but it is pointing along the y-axis. So if you have also the z-axis, the k hat points along the uh, so the XYZ, this is the Cartesian coordinate system, right-handed Cartesian coordinate system. So this unit vector has, yeah, sometimes that some people have the name, but they don't have the quality like that. So unit vector has no units. That is the thing. Like some people say Sugandhami, but yeah, problem there. Now the unit vector has no units. It has no units. It has just magnitude of 1. Like this, it has no units, no any SI units or any other units. It has no, yeah, it no has no dimensions. Um, yeah, sole purpose of it is pointing in a certain direction of the axis. So if you have this unit vector, you can write uh, any vector in terms of unit vectors. Here there is an example for the position vector. You know the position vector, right? You learned this long time. Maybe not that long time, but yeah. Yeah, it is now actually significantly long because you had long holiday and yeah. But you can take the notes and check it again. That is, you know what is a position vector or displacement vector. So if you have a displacement vector R, here you see the arrow R, you can write it in terms of unit vectors. R equal the distance along x-axis, distance along y-axis, distance along z-axis, but you cannot just add them because these are vectors, because they are perpendicular to each other. So you can write the vector R like this, -3 along, there's -3 I hat, that is the distance. So here where the particle is, let's say there's a particle at this point. So the coordinates of that particle is -3 to 5, right? So you have to go -3 along x-axis, -3i, 2 along y-axis, 2 meter j, and to come to the particle, you have, so this vector has been, that is decomposed into its components, x, y, and also z. So you can write the vector r in terms of unit vectors like this. Everyone understand that? So the coordinates of this particle here you see, is -3 meters, 2 meters, 5 meters. So if you write the vector in terms of unit vectors, it looks something like that. So the unit vector itself has no units, but the term in front of it has the units. Here in this case, it is the position. Position is measured in meters, so it has the units of meters, and so on. But remember, you cannot just add these three numbers because it's a vector. You have to use that is, if you want to find the length of R, you have to use the Pythagoras-like formula. That is this squared plus this squared plus this squared to find the magnitude of R. Here, the direction in this case has two angles, the theta and phi, so I'm not going into that because it's a three-dimensional coordinate system in this example. Yeah. Any questions? Everyone understand? So this each vector has a magnitude of 1, the I hat, j hat, and k hat. And the sole purpose of it is pointing. That is pointing, that's your magnitude is along which axis. So -3 is along x-axis. That's why it is I hat. and so on. 2 meter magnitude along uh, y-axis, and also the z-axis, the k. So this doesn't have to be position or the displacement. It can be the velocity, it can be the acceleration, it can be. So also you don't have to have all three axes. Maybe you can have two axes if it is, if your particle or whatever is moving in 2 dimensions. But in this case, yeah, it took 3 dimensions. All right. Any questions up to now? No? So you can read this. This is also important for engineers and the technologists. Yeah, it involves certain amount of mathematics, unit vectors, and stuff. Right? Yeah, here it says this is how much it went along x-axis, how much y-axis. So you can read it. So I put this updated notes also into LMS. And also you can represent here using R hat notation. You can represent a vector. Like, for example, in 2D, yeah, maybe I should have put the vector. Anyhow, yeah. So depending on which quadrant you are in, you can define a new unit vector called R hat like this. But depending on the which quadrant you are in, this plus and minus sign changes. So because you are not always pointing exactly along x or y, you can have a unit vector called r hat also. R hat, you can write it as cos theta I hat plus sin theta j. Like, yeah, this is just for the back. Yeah, maybe I can, in the future lectures, maybe we can discuss further. So can you find the magnitude of vector r hat? You just have to take the x component squared, y component squared, and add them using the Pythagoras formula. And take the, what is the cos theta squared plus sin theta squared? What is the value? Cos theta squared plus sin theta squared? 1. So r hat is also a unit vector, but it is not necessarily pointing along x or y direction. It is pointing along uh, random direction, that is with an angle theta. So depending on the quadrant you are in, so you can write any vector in terms of the magnitude of that vector. Like there's a 5 Newton force, 5 Newton time R. But depending on which quadrant you are in, so if you're in the first quadrant, both these cos theta and sin theta both are positive uh, of your r hat. If you are in the second quadrant, your cos theta is negative, sin theta positive. So it is same as the components. So using r hat notation, also you can represent any vector if you know the magnitude. So r hat also what it does is it just points in which direction uh, your vector is. Right? All right. So you can read that also. Yeah, depending on the quadrant, uh, the sign of your r hat, the x component and y component, either is plus plus or plus minus plus, so plus minus or minus minus, depending on which direction your r hat unit vector is pointing. Right. All right. Yes, this is an example, another example. Uh, so if you know this r hat unit vector, you can find the average velocity. That is, if you know the displacement, you can find the average instantaneous velocity and average velocity. Uh, and you can write it in the unit vector form like this, where Vx is dx over dt, Vy is dy over dt, Vz is. So the velocity V can be written, R is the position vector or the displacement vector. Actually, the delta R is the displacement vector, right? So remember, we did these things, but not in the vector form because we only covered previously one covered the one-dimensional case. But if you are in 2 dimension or 3 dimensions, you have to represent the position vector as a vector, that position as a vector. This is the average velocity. So similar to the 1 dimension, only difference is you have vector sign here. And you take the d over dt, then of the displacement, that is the position, then you get the velocity. Also, you can find the acceleration by taking the derivative of this velocity, right? But as you can see, you can write the velocity in terms of its components. In the I hat direction, that is the x direction, j hat or the y direction, k hat z direction. So if you have only two, if it is the particle is or whatever car is moving 2 dimension, you can ignore the k hat. And right here, the average instantaneous. And if a particle is moving in a certain path, you can, for example, this is the xy coordinate system. The velocity is always tangent to the motion of the path. Right? Then you can, that is, it's along the, uh, this is the path you see. Some particle moving along, maybe a projectile or whatever motion, any motion. So here we are not very, that is, we are not specifying what kind of is it projectile motion or circular motion, or it is just generalized. Any kind of motion, you can represent the velocity is always along the path. It is said to be tangent to the path, particles path. Velocity of the, because remember, velocity is not the speed, it has a direction. And you can find the x and y components by taking the cosine and sine of the v. Here there is an example. Maybe you can read the example and do it. I'll put this on the LMS. You can read it and come when you come to the next class. Maybe I can briefly go through it. All right. So if a electron's position is given by this vector, so now the position vector is given because it is not just one-dimensional motion, straight line motion, it is 3-dimensional motion. So, yeah, probably more than one. So T is in seconds and R is in. So can you find the velocity Vt in unit vector notation? So if you have your notebooks or piece of paper, you can do that. So what is the electron's velocity? So you just have to take the derivative of dr over dt, and you do the derivative for each component. The I hat component, j hat component, k hat separately. So here I put the answer also. So this is the now the position vector is a bit more complicated. It is not just one dimensional. It is more than one dimension, like even three dimensions. But the velocity equation, remember v equal, earlier you just did dx over dt, right? But now we use dr over dt because my r is now more general. It is not just along x-axis. It can be on, that is, it can be pointing at any direction in your XYZ coordinate system. So to find the velocity, again, you just take the derivative, but now instead of x, you have r vector. And here you take the derivative of the first one. So 3t, what is the derivative of 3t? Just 3, right? When you take the derivative with dt over dt is 1. And here t square, when you take the derivative, it becomes 2t. So 8t. And k, this one disappears because this is a constant. So the component along the z-axis, velocity component is 0. So this is the velocity in unit vector notation of that particle at time t. We put the units meters per second. And at 2 seconds, well, it is asking what is the velocity. So to find the at 2 seconds, you instead of t, you put 2. So it times 2 is 16. And that is the value. And at 2 seconds, what is the velocity? Not the vector, but the magnitude. So you use the Pythagoras formula and x component squared. You cannot just add these two because they are along different axes. That is 3 minus 16 is not minus 30. You have to use the vector algebra. And there where you use the Pythagoras formula. 3 squared minus 16 squared equals 16.3 meters per second. Yeah, you have to use a calculator and here, the angle. One student previously asked, what about negative, right? Now, let's see here. There's an example. So to find the theta angle, uh, so the particle moves with that angle because it is always tangent to the path velocity. So you use the y component of the, yeah, here there is here y component of meters per second, 16, x component, yeah, actually, yeah, even the y over x, it has to be vy over x, meters per second. And yeah, somehow you get a minus, and yeah, you get actually two angles. But you see here, what component is positive and what component is negative? X component positive or negative? Yeah, one student says he just now, no problem with that. Yeah, I will. You can read the notes and I will try to put this on the limits also. And yeah, here you get a negative. If tan is negative, now what the hell? So you see here the x component of the velocity is positive, y component is negative. So which quadrant is it in? X component positive 3, y component negative. Which quadrant? So it has to be in the fourth quadrant, right? Yes, exactly. Some people are very carefully listening to my lecture. Very good. Yeah, so it has to be in the fourth quadrant. So if you are in the fourth quadrant, uh, angle you can calculate, because the angle should be between 270 and 360, but in the calculator, most likely you will get negative whatever. But yeah, since yeah, that's also okay, you can leave it as, but it cannot be this one, not the positive 101. It has to be this negative 79 because it's in the fourth quadrant, but in another way to write it is 360 minus negative 79.4. So this is wrong answer because it represents which quadrant? 101. It is representing the second quadrant, but actually we are in the fourth quadrant. You can try it with your calculator. Everyone understand that? Maybe that answered that student's question that one student previously asked, that what happens if tan is negative? Yeah, this one actually answers that. Right? So if tan is negative, it's either in the second quadrant or in the fourth quadrant. But since here the x component is positive, it has to be in the fourth quadrant. In the fourth quadrant, the angle should be either you can say it is minus 79, taking the small angle, but also you can write it as 280. Because in the fourth quadrant, it has to be between 270 and 360. How come 101 degree tan hours? Because Buddha, I think in the calculator, you get one student is asking how 101. So this one you have to, it depends upon your calculator actually. Uh, so sometimes in some calculators, it will give both answers. Because this negative one is actually not known by, because here there is a negative and negative tan. These both answers are correct, right? Both answers are correct. But since by looking, because the x component is positive, only you can tell that, because in a calculator, when you calculate it, actually these both answers are actually correct for the calculator, because it doesn't know that the x component is positive, because once you divide 16, that is minus 16 by here, switch minus 16 by 3, then it just gives a negative number. So for the calculator, these both are correct. But you have to understand the only correct answer is this one, because the x component is positive. Right. You ask questions, it is very important because you are someday supposed to be a technological engineer or engineering technologist, or just an engineer or somehow in engineering. Or at least you will be teaching this thing in a school or university or wherever. So learn everything properly. Uh, yeah, there are now adding vectors by components. There are more stuff. Yeah, there are more stuff. Maybe we can go on this tomorrow. And I'm not sure what will happen tomorrow. Maybe I would have to do it online, because I heard that very bad situation in Kamrupiti. Yeah, you can read and come. I'll put all this. Yeah, actually, yeah, the vectors you have to know very well, because if you are telling you are a STEM graduate and you don't know about vectors, that would be a big shame. Yeah, these are the next lectures. We'll come to that after doing these things. So I'll put the vector notes into LMS and you can read. And I think you can't do this tutorial. You can start on it. Yeah, I'll put the tutorial also. You can start working on it, but maybe you have to wait till tomorrow to or week after that. Let's see. All right. All right. So if you have any questions, you can ask me now. You can read this and come, because now next we have, that is how to add vectors using this unit vector notation. Very simple. You just have to just add the components. You can just look at the examples. You can look at them and come, read it and come. All right. That's the next part we have to go. And next we have to come to multiplying vectors also. So definitely we need another more lecture tomorrow or next week. Yeah, you can read it and come. What are cross products, dot products? That is multiplying vectors. Yeah. So yeah, up to now, if you have any questions up to the things we did up to now, maybe in the unit vectors, this slide got skipped, no? Yeah, this slide I think got skipped somehow. Yeah, this is just represent, as I told, the unit vectors are that a vector A can be represented in terms of a unit vector. Um, Ax, so Ax, Ay, Az are the scalar magnitudes along each axis, and you just multiply that by I hat, j hat, k hat, and you get the vector A, in which, yeah, same thing. So if there's a vector A, you can resolve it into three components and represent it using the unit vector notation, like. Okay, so if there is no any questions, I will stop now. And tomorrow also, I think we might have to go through that is online mode. But if the water goes down and the department says everything is good, then we can do it offline. All right. All right. And let me stop this. All right.
Recording stopped.
Okay. So maybe you are having the chemistry class also after this online. I'm not sure what happened there. Uh, you have a chemistry class, no? Today, I think, right? Yeah, that whatever you have to resolve with that lecture. So I will stop for now, and as I told, I will put the notes onto LMS, and also try to put the tutorial, because the tutorial tutorial maybe you need maybe we might have to wait till next week, because I have to do some tutorial classes also. Tutorial as part of 6, and part of that is tutorial 7, the whole tutorial. And tutorial 8, you I think you submitted it on this Friday, last Friday, right? Yes. Okay, so I'll stop now if you don't have any questions. So as I told, now it's time to prepare for the quiz number 3, and also especially the end semester exam. You can download the past papers, get the past papers from the library, and do those questions. Um, Currently, yeah, you can do a lot, almost everything. Because one of the time I finished, because there was no time during COVID, and we had only 6 or 7 weeks, and somehow. But remember this, everything is someday you will use, but for the exams, uh, most of the stuff has been done. All right. No questions? Then I will stop. All right.